Hi, my name is Chase Wood. I'm an applications engineer with the high-speed data converters team at Texas Instruments. As we know, VNAs are used to evaluate or analyze a system or network. This piece of equipment works by providing an excitation signal into a user-specified port or net of a system and measuring the response at another user-specified port of the same system, all while varying the frequency of the excitation signal to produce what are known as S parameters. These S parameters represent the amount of power passable from any excitation port I to the measured port J. As an applications engineer, I use a network analyzer very frequently to evaluate or validate some components before making the decision to include them into my evaluation hardware kit. What I'll be showing here today is more so focused on the automation aspect of controlling a network analyzer remotely, which is something that I often use in a day-to-day environment. This is made possible using SCPI commands, also referenced as SCPI commands, throughout the remainder of this video. Let's first get started by launching the network analyzer simulation software. I'll be choosing a PNA-L as my VNA of choice, specifically only interested in measuring a 2-port device to around 8 GHz or so, meaning the 2-port N5231B supporting up to 13 GHz is sufficient. After opening the simulator, let me begin by pressing Preset to reset the state of the VNA to the factory preset. Let's assume that I'm a system designer and I'm in the search of a wideband balun for my receiver front end. But before designing in any in particular single-ended to differential converter, it would be nice to first measure a sample component from the vendor to see if it actually is sufficient for my application. It's important to note that I've replaced the default DUT with actual measured S parameters for the Marquee microwave balun I'm considering. The first measurement I would like to take is a simple S11 measurement showing the amount of power this balun reflects back towards the incoming single-ended signal. I'll make this first measurement manually using the buttons on the test equipment. First, I will select stimulus and change the upper frequency range from 13.5 GHz down to 6 GHz. My balun is only 3 GHz, however I'd like to see how it performs beyond 3 GHz to take into consideration any higher frequency spurious. After doing so, I will then change the step size from 67 MHz to 1 MHz so my measurement has a fine resolution. Next, I will set the measurement to be S11 by clicking on the measure button and then selecting S11 using the soft button. Last but not least, I will enter the trigger menu and select single shot capture so the data I eventually save is a continuous and completed sweep. So far, this looks reasonable. My return loss looks to be between 10 to 15 dB or so. Let's actually set the scale to see this a bit better. Ideally, I would prefer to see return loss a bit closer to 20 dB, but as this is a high linearity and wideband device, this should be acceptable. The next measurement I want to take is S21. This is often referred to as insertion loss for passive devices, but can be generalized as forward gain. This represents the amount of power gained or lost within the network itself while passing from the input to the output. As I mentioned before, the remaining measurements will be automated using SCPI commands. My preferred language of choice is Python, and as a result I will be using the PyVisa package. After first learning what the VISA device address for the VNA in the simulator was, I was able to quickly create a script for automating the S parameter measurements. Let me quickly overview this script before we run it. First, we have the user parameter section. In this area, the user must define the VISA device address, the VNA model number, frequency stimuli, a list of desired S parameter measurements to take, and a few other settings. After the user parameter section, I then connect to the provided VISA device address and cross-check that the user is connected to the correct device by reading back the identification. This should contain the VNA model number, and if the device is not as expected, then a warning message will be displayed to the user. Next, we will iterate through this loop for each S parameter in the user-defined S parameter list. At the start, we set a new trace and assign a reference name as the active S parameter measurement. In step 2, I set the start and stop frequency for my excitation signal, and optionally set the step size here as well. Step 3 is simply to auto-scale the window on each iteration. Step 4 changes the trigger from run continuous to single shot mode, so the data that I save in step 5 is a full capture. Let me first toggle preset on the VNA so everyone can see how the trace from our previous S11 measurement disappears. And now if I run my Python script, we will see a few brief flashes and then all the traces will be on. Having a decent automation environment enables rapid validation of components by allowing us to simply connect our new devices to the VNA input ports and to run the same automation script that we've had before. All code that I have written for this video demonstration will be available on GitHub, and the link is in the description below. If you have any questions or comments about this, please leave me a comment below, and I will get back with you as soon as I notice it. Thanks for watching, and enjoy the rest of your day.